A special type of neural network that has gained a lot of attention in the age of deep learning is the convolutional neural network. Now this differs from a standard fully connected feed-forward multi-layer perceptron in terms of its basic structure and how the weights are set up, and is typically applied to image problems, which is what I'll be showing in this video, and then in a later video we'll see how they can be used in other ways. So a standard problem that you might apply a convolutional neural network to would be to look at images of numbers and to classify them, in other words determine which digit is depicted here. Now as humans we can see that this is a 4, but I've drawn it on this grid, and this is a 10 by 10 grid, and so these are the individual pixels. So the idea is that we will have a convolutional network look at the raw pixel input of an image and then determine what is in the image. Now in this case, if we're only going to give it numbers, it would have 10 possible classifications, the digits 0 through 9. This is a very challenging problem, especially when you realize that a real image, rather than this example image, could be much larger. And so that makes for a massive input space, which makes for a larger network, which means there's more weights to learn. So how does a convolutional neural network tackle a problem like this? First, I'll define the concept of a receptive field, also known as a kernel or a convolutional filter. So these squares that I've highlighted in red are an example of a 3 by 3 receptive field. So it's called a receptive field because there will be a specific neuron in a hidden layer above the inputs that responds to those input values. So these are the local neurons, or this is the local region of the input to which a particular neuron will be receptive. So if we draw a portion of the next layer of the input, this, for example, would be part of the hidden layer that is above this input layer. We would have a particular neuron here that is connected to those 9 input neurons by links, like so. And now that these links are in place, we can discuss how the remaining links in the network are structured. Essentially, we will take this receptive field and slide it across the input space, and then once we reach the end, we will go back to the start, but down a row, and then slide it across that way too. Each receptive field that we create on the input space will correspond to a neuron in the hidden layer. So what I'm going to do is remove these links in this receptive field and show what the next one adjacent to it looks like. So here I have shifted the entire receptive field 1 pixel to the right, and as a result, in the hidden layer above the inputs, these 9 neurons are feeding their values into the neuron that is 1 pixel to the right in the hidden layer above. And you can see that this will continue across this entire space. And note that this input space is 10 pixels wide, but this hidden layer is only 8 pixels wide. And that is because with a 3 by 3 receptive field, we will only be able to move the receptive field enough times to the right to hit 8 different points on this hidden layer. The reason that we move only 1 space as opposed to more is because we are using a stride of 1. So stride is a parameter you can set. If my stride were 2, then I would move 2 pixels to the right instead of 1. Typically, you want to have some overlap in your receptive fields. With a 3 by 3 receptive field, if I had a stride of 3, then I would have no overlap at all, which would be undesirable. Now just to remind you once again, note that when I have reached the far right, I will also go back to the beginning, move down one, and resume the process. As a result, the receptive fields will cover the input space, and all of these hidden neurons will receive an input. However, we don't have only one group of neurons in the hidden layer. We will have several, and each one will be the same size, and we can think of these three separate squares of neurons as being stacked into a three-dimensional volume. Now, each of these squares corresponds to a different convolutional filter. Now, when I was drawing these links, notice that I used the same color, red, for the links in the first 3x3 receptive field and the next one. That is because the values of those weights will actually, typically, be identical. This is known as weight sharing. Weight sharing reduces the parameter space of the convolutional neural network, but also serves the purpose of creating a convolutional filter that looks for specific features in the input. A certain configuration of weights for this 3x3 receptive field corresponds to a certain organization of pixels in the input. And by sliding that fixed set of weights across the whole image, what we essentially do in this next layer up is create a map for wherever that feature appears. I'll be going into this in more detail in a moment, but first let me just focus on the structure of the network a bit more. So as I said, there are three separate squares here, each corresponding to different convolutional filters. As with this red filter, we had a receptive field here that fed into that first neuron. The one that is still shown here feeds into the second one, and it slides all the way across this so that all of these neurons have an input. Likewise, we will do the exact same thing, except feed the links into these filters, like so. So here we see some examples of where the links would go in these different parts of the hidden layer. So just remember that each of these filters actually covers the entire input space. But just as an example, if we had a 3x3 local receptive field here, the particular neuron in the hidden layer that it would go to is this one, which is on the far right and one down. And for a local receptive field here, that is one in from the right and one up from the bottom, we would likewise have a target hidden neuron that is also one from the right and one up from the bottom. Each of these filters covers the entire input space and creates what's called a feature map of where that particular feature is present in the input. So let's see an example of how a filter that is moved across the input space can create a feature map in the layer above it. Before showing how these feature maps work, let me just clarify that all of the neurons in a convolutional network behave in exactly the same manner as they do in a standard multilayer perceptron. We have each of these neurons receiving inputs from links in the previous layer. Those links have weights. At the neurons, we compute a weighted sum. The neurons also have a bias, and there's also an activation function. So that's all the same. But in this diagram, I'm going to represent the numeric link weights with colors. So basically, the dark, fully colored in points represent a 1, and the white, empty spots represent a 0. And that's true of the input space as well. So we can think of this input space as consisting of mostly zeros, but of 1s at these particular locations. Now this is the filter that is used by all the neurons in this feature map. So this filter slides across the input, and so remember we have 9 links coming out of this, and what this filter is showing is that the link weights that exit these 3 locations will have a value of 1. Now, we're only using values of 1 and 0 in this example to make it simple to show what's going on, but the weights can of course be any value as in a standard neural network. So, if I slide this filter across the input space, what happens? Well, when the filter is on this 3x3 receptive field of all 0 inputs, we will have 0 times 0 for each of those weights, and then 0 times 1 for each of those. And if for now we simply ignore the bias, assume it's 0, that means that we will have an output from this neuron also of 0 before the activation function transforms it. But if we slide over 1 to the right, well, then what happens? Well, we're touching this point. So this input value of 1 gets multiplied by that value of 1. Those 2 points, which correspond to those 0 inputs, are not activated. So we have a non-zero result here, but we could have had a higher result. So what this means is that this filter is maximally activated whenever the receptive field, or the filter, is located directly on a portion of the input that matches it. So when I have this filter located right here, this 3x3 area here will contain these 3 input values of 1, which match up with these 3 weight values of 1. So that means that the activation in this feature map will be the highest value it can possibly be at that point. So now I will fill in this feature map to demonstrate that point. So what I've done here is, for any hidden neuron in this feature map for which all 3 of those positions have a value of 1 in the input, I've completely filled in the square for that neuron. If 2 of the 3 are present, I've filled in the lower right corner, and if only 1 is present, then I've done a little triangle on the bottom. We can see, for example, when the receptive field is centered on that neuron, that will correspond to this hidden neuron, and we only have 1 active point detected there. And if we go down, we have 2 input points, and so the activation increases at that point, which is beneath this one. And then if we go down to this neuron, now all 3 of those inputs are activating. They're combining with those weights to get the maximal value here, so that neuron is fully colored in. But then when we move down 1 more spot, now we have this lower right corner going off the edge and not detecting an input, so our activation here is lower again. Now notice that if we move to the right twice and we're centered at this point, that there'll be inputs here and here which are ignored by this filter. The weights on this filter are 0, so the fact that those positions are activated is irrelevant. However, those 3 spots are present and they correspond to those 3 weights, which is why we get the maximal activation here, and we also get it up and down. So whenever the receptive field is centered on this spot, or this spot, we overlap with those 3 inputs, those 3 inputs, or those 3 inputs, which is why we get the maximal activation in those spots. And so this is called a feature map because we're essentially looking for the presence of this organization of inputs within the greater input space. This is a vertical line detector. This tells us all the points where we have a complete vertical line, and it also tells us points where we have something close to a vertical line, albeit with slightly lower activation in the feature map. I will repeat this process with the next 2 feature maps. So here we have a feature map for the green filter and a feature map for the blue filter. Now the green filter is complicated. It's looking for this reverse L shape, and so its highest activation is only at those 2 points. those points correspond to the centers of this receptive field and that receptive field, because we have the L shape there and there, which maximally activates those 2 points. The other activations are partial because we don't have full correspondence between the filter and the inputs. For the blue, we have a very simple filter because all this does is essentially take the input and then shift it in the hidden feature map. We have exactly a 4 here, which is moved to the right, or perhaps you can think of it as simply chopping off part of the border of the input space around it. So why is this useful? Well, remember that the whole point of this convolutional neural network is to take inputs of numerical digits and tell us which one we actually have. This is only the first of many hidden layers. For a complete convolutional neural network to successfully classify that digit, we need several layers. And so now that we've gone over the low-level mechanics of how these filters slide across the input space, let's start drawing more abstract diagrams so we can have a depiction of the entire neural network which is capable of solving this problem. And here is the architecture of one of the first truly successful deep convolutional neural networks. It is called LeNet because the first author on the paper where it was presented was Yann LeCun, and so it is his network architecture, and it was used to classify handwritten digits. The actual image size was a bit larger than in our previous example. All of the inputs were 32 by 32 pixels. So we had a single input layer with 32 by 32 pixels. Every example had a digit 0 through 9, and the activation values in this input field were 0 to 1, representing pixel intensity values. So if someone is writing a digit, they are not going to have perfect pressure on the pen the whole time, and so some strokes are weaker, and those end up appearing as slightly grayer parts of the depicted image. So the image is in grayscale with the intensity value from 0 to 1 indicating how dark it is. The next layer of the network is a convolutional layer, as we saw previously. Each of these convolutional layers is 28 by 28 pixels. The reason that that is the size is because 5 by 5 receptive fields are used with a stride of 1. And so if a 5 by 5 convolutional filter or receptive field moves across this input space, then you will lose 2 pixels on the left, right, top, and bottom sides of the image. And so that's why a total of 4 pixels is subtracted to get 28 by 28 feature maps. The next layer is something we actually haven't talked about, but I'll clarify in a moment. It is known as a pooling or subsampling layer. The point of pooling layers is dimensionality reduction. Note that with 28 by 28 feature maps, we have a lot of neurons whose activations we have to process. And so the point of a pooling layer is to reduce the dimensionality by looking at small regions of adjacent pixels and reducing them to a single value. Specifically, for every 2 by 2 area in these feature maps, in other words, for every 4 neuron activations, those get reduced to a single neuron activation, because the stride with a pooling layer actually should not allow overlaps of the receptive field. Once again, I'll clarify this more in a moment. And so what we have is a way of dividing the feature map size by 2. So notice that there are 6 feature maps here. In this pooling layer, there are also 6 feature maps, but we go from 28 by 28 to 14 by 14. After that, we have another convolutional layer, and this convolutional layer behaves the same as the other one, except it is on the pooling layer. The convolution filter size is once again 5 by 5. The stride is once again 1. Although this time, if you actually count all of these out, you'll see that we have 16 feature maps. So although we are getting smaller and smaller feature maps, we are making more of them so we can extract more different features. Each of these is 10 by 10 neurons in size. Then we have another pooling layer for the sake of dimensionality reduction. So we still have 16 feature maps, but these are 5 by 5 in size because the stride is 2 and the filter size for that step to the pooling layer is once again 2 by 2. Next, we have dense or fully connected layers. This is basically just a standard multi-layer perceptron. The logic behind this is that a feature map is, as the name implies, a bunch of information about the locations of features in the image. So the whole point of all of these convolutional operations and filters is to take the raw input and extract useful features. Once we have extracted useful features up here at this pooling layer, we then process those features the standard way that we would with a fully connected feed-forward multi-layer perceptron. This is just a multi-layer perceptron with 2 hidden layers. There's 120 neurons in that hidden layer, 84 neurons in that hidden layer, and then the output layer has 10 neurons. These are feature maps, and each of the neurons in these 5 by 5 feature maps connects to all the neurons in this layer here. Now the reason we have 10 outputs is because we are classifying written digits. So there are 10 possible ways to classify each digit, 0 through 9. For any given input that you provide here, you will get 10 outputs, one of which will be larger than the others. And so each of these outputs corresponds to one of the possible digits, and whichever output is largest is the one that the network uses to label that input example. And so that is the architecture of LeNet, and there are actually much deeper architectures now in the modern world of deep learning. But this was an early and quite revolutionary approach to extracting raw features from an input image using convolutions, reducing dimensionality with pooling layers, and then doing some final processing with fully connected dense layers. So now let's take a step back, clarify what pooling layers are and why they work, and then see a few more examples of what convolutional neural networks can do. Simply put, a pooling layer would take, for example, a 4 by 4 map like this and reduce it to a 2 by map, assuming 2 by 2 receptive fields. This group of 4 numbers would be reduced to a single number here. This group would be reduced to a single number here. Those 4 would go here, and those 4 would go here. So how does the pooling operation work? Well, it depends. There are several different pooling operations. One of the most common is max pooling. In max pooling, the largest value in every 2 by 2 group of 4 would become the value in this next layer here. So we have raw numbers here to make this point, 0, 1, 2, and 5. 5 is the largest, so 5 would go there. Within this group we have 2, 2, 3, 3, so 3 would go here. In this group we have 0, 0, 0, 8, so 8 would go here. And here we have 2, 3, 4, 5, so we would have a 5 again. Now clearly we've lost some information in making this reduction, but it tends to work, and it is to some extent necessary for practical purposes. However, there has been some recent controversy about the long-term viability of convolutional neural networks as image classifiers because of uses of operations like max pooling and other pooling operations in general. Of course, we don't have to use max pooling. There are other options. You could use average pooling, in which case you would take each group of 4 numbers, 1, 2, 0, and 5, and take their average, and that would be the value in the next cell. Specifically, 5 plus 0 plus 2 plus 1 is 8, divided by 4 is 2. 3 plus 3 plus 2 plus 2 is 10, divided by 4 is 2.5. 8 divided by 4 is 2, and these numbers, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, divided by 4 would be 3.5. So that's average pooling. You can also have weights on the links and have those be learned, and the weights on the links would affect the actual calculation. What's important though is that you get dimensionality reduction by taking groups of pixels or neuron outputs and reducing them into a single output. To wrap up, let me just point out that we don't have to limit ourselves to black and white images. Here the input is pixel intensities, but if we have a standard color image, we can split it into 3 we call channels. So now our input has 3 separate maps or channels, and these would correspond to the 3 different color components in any image: red, green, and blue. Every pixel is a mixture of 3 colors, and each of those intensities is a single number, which makes this easy to use by a neural network. In fact, we don't have to limit ourselves to 2-dimensional images. We can even use 3-dimensional data and classify information about point clouds. There are also various other tricks that can be done to complicate but improve the performance of all of these steps in the various hidden layers of deep networks. But those enhancements are outside of the scope of this video.